first problem of the sheet is about a person standing on the top of a building, throws two balls, A and B. The ball A is thrown up with a speed u, whereas the ball B is thrown down with a speed u. Now, after a while, both of them hit the ground at some point P, and A hits with a velocity VA and B hits with a velocity VB. We want to be able to compare A and VA and VB. Now, very clearly, what I do is A or B. I choose everything in this direction positive and everything in this direction negative. All right. Now, on hitting the ground, let's say the velocity with which it hits the ground, A or B, let's say is V. So V squared. Now, let me look at B for example. It hits with a velocity V, say. So V squared minus U squared, I'll take plus U because I've taken downward positive. So minus U squared is 2, G will be taken positive, downward positive, and H is measured from B towards P. So positive, H is downwards and positive displacement with respect to B. So H. That's as far as B is concerned. So as far as A is concerned, everything remains the same. Instead of U, you have minus U. Instead of U, you have minus U. This is VB, say. And VA squared. A hits with a velocity VA. VA squared minus U squared. A is launched with a velocity U upwards. So in that formula, U to be replaced by minus U equals 2G. And its displacement once again is H downwards. No matter how it goes from this point to this point, the net displacement is H downwards. So H. Very clearly from these two equations, nothing changes. VA is evidently equal to VB. VA is evidently equal to VB. A and B hit the ground with the same velocity. Yes or no? I'm assuming you would have got it right independently as well. In both cases, the displacement is H downwards. No matter how I'm chucking the ball, the displacement is H downwards. Problem number 2, we have an instance of a velocity time graph. Velocity in meters per second versus time in seconds. And this is how the graph looks. This is, I guess, 2, and the upper height of this is 1, 0, 3 seconds, 4 seconds, 5 seconds. This is the velocity time graph given, and this is -2, I guess. This looks like -2, right? This is the velocity time graph. We want to be able to find the displacement. We want to be able to find the total displacement. The total displacement would be the area, algebraic area under the velocity time graph. Now, which is this area. So the areas above the horizontal axis, positive. The areas below the horizontal axis, negative. So this area very clearly, what is this area? Half of 3 into 2 is this area. Yes or no? Half of 3 into 2 units, half of base into altitude. Positive. Then this area very clearly 2 into 1. This is 2 units into 1 unit, but negative, right? So minus half of 2 into 1 is this area, subtracted because it's below the time axis, and then plus this area. This is 1 unit into 1 unit. Yes or no? That's a displacement. That's a displacement. Yes or no? Clear? Problem number 3. A particle moves along the x-axis and its x coordinate as a function of time is given by u into t minus 2 plus a into t minus 2 whole square. A into t minus 2 whole square. That's position x, x coordinate as a function of time. Now, the initial velocity of the particle. Now, when they say initial velocity, what is meant is velocity at time t equal to 0. And it doesn't necessarily mean that the motion started at t equal to 0. The motion might have prevailed prior to t equal to 0 as well. One way or the other, the velocity at any given instant of time is given by dx dt, rate of change of x with time. So this is like, I differentiate u, derivative of this will be 1, yes or no? Plus 2a into t minus 2. How about it? Do you realize what I did here? Derivative, a is a constant, so derivative of t minus 2 whole squared with respect to t from chain rule. With respect to t minus 2, it's going to be t into 2 minus t minus 2, and t minus 2 with respect to t is going to be 1. Yes or no? So, at velocity at time t equal to 0, just plug in t equal to 0 here, you get u minus 4a. u minus 4a is the velocity at time t equal to 0, referred to as the initial velocity. Yes or no? Put t equal to 0. So u minus 4a, which is the initial velocity. Sounds all right? Now, if you differentiate velocity with respect to time, you will get acceleration. Are you confused? Right? So what is acceleration at any given instant of time? Differentiating velocity with respect to time. If you differentiate velocity, this will be 0. This will be 2a into 1. Right? So acceleration would be 2a meters per second square. Right? So velocity at time t equal to 0 is u minus 4a. Acceleration is 2a. Yes or no? So, shall we proceed? Can I wipe this off? Huh? I think they have goofed it up, you know, while typing. It's all goofed up, but does not matter, you know. Whatever might have been the options. Initial velocity of the particle is not u, but is u minus 4a. Acceleration of the particle is a. Acceleration of the particle is actually 2a. 2a. So, you know, option C, which is written as 2s, actually should be 2a. At t equal to 2 seconds, the particle is at the origin. Yes. If you plug in t equal to 2 in the original equation, x becomes 0. So option D is also right. At x equal to 2 seconds, the particle is indeed at the origin. So we have option C right, provided this 2s is 2a, right? And option D is right. At t equal to 2 seconds, the particle is at the origin. Clear? Can I wipe this off? Number 4. Option A, we want to choose the correct options from various options that are given. Option A, velocity and acceleration velocity and acceleration have opposite signs, the object is slowing down. What it clearly means is that if velocity is in one direction and acceleration is in the opposite direction, there is retardation. Very clearly there is retardation. If they have opposite signs, they would be directed oppositely. Acceleration will kill the velocity till such time that the velocity becomes zero, right? So velocity decreases, the body slows down. The body indeed slows down, right? So option A is right. Option A is right. If the position and velocity have opposite signs, say in the xy plane, there is a particle here. This is its position vector r. From O to P is its position vector r, right? This vector is r. And if its velocity is opposite to the position, that means this. R is in this direction, but velocity is in this direction. Very clearly the particle must be moving towards the origin. Very clearly the particle must be moving towards the origin. So option B is also true. Option B is also true. Position and velocity have opposite signs. Very clearly R and V have opposite signs here. The particle must be moving towards the origin. Option B is also true. Option C. If the velocity is zero at a given instant, if the velocity is zero at an instant, the acceleration should be zero at that instant. Is that true? No. Velocity might be zero, but the rate of change of velocity may not be zero. And rate of change of velocity is acceleration. Like it happens for a particle which is chucked up at the highest point. Its velocity becomes zero, but its acceleration is still g. So velocity might become zero at a given instant, doesn't mean that the acceleration is zero. Got me? Rate of change of velocity need not be zero at that instant. Got me? So it's not true. Velocity zero does not mean that acceleration is zero, right? And if acceleration is zero, does it mean that velocity is zero? If acceleration at a given instant is zero, no. The particle could have been moving with a constant velocity. Okay. Option D. If velocity is zero for a time interval, if velocity is zero for a time interval, acceleration is zero at any instant within the time interval. Yes, yes. If, let's say between t equal to t1 and t equal to t2, velocity is zero over a time interval, not at an instant, but over a span of time. If the velocity is zero, then acceleration also is zero, right? So option D is true. Option D is also true. A motor car is going due north at a speed of 50 kilometers per hour. Right? And it makes a 90 degrees left turn without changing the speed. This is let's say velocity v1, and then its velocity becomes v2. v1 is directed upwards, v2 is directed eastwards, right? The change in velocity of the car. Change in velocity is delta v, which is final velocity minus initial velocity. That means it's a resultant of v2 and negative of v1. It's a resultant of v2 and negative of v1. v2 is still 50 kilometers per hour. This is v2, 50 kilometers per hour leftwards, right? And minus v1. If v1 is 50 kilometers per hour upwards, minus v1 would be 50 kilometers per hour downwards. So this would be minus v1, which is 50 kilometers per hour downwards, and the resultant of v2 and minus v1. v2 and minus v1 would be v2 minus v1, which would be change in velocity. Yes or no? So change in velocity is the resultant of v2 and minus v1, and the resultant of these two very clearly is this vector, which is 50 root 2 Isn't it? This would be 50 root 2. If this is 50, this is 50, 50 root 2 kilometers per hour. And evidently each of these angles would be 45 degrees. This is 45 degrees, 45 degrees. Yes or no? So 52 kilometers per hour. What's the direction? What is this? This is east, isn't it? This is south. So this is southeast, southeast, isn't it? Southwest. Oh, sorry, this is west. This is west. This is west, leftwards west. So this would be southwest. 50 root 2 southwest. 50 root 2 southwest. So far so good, right? Two objects moving in the same straight line are leaving a point A. This is a point A. With accelerations A and 2A respectively. One has an acceleration A. The other one has an acceleration 2A. And with velocities 2u and u respectively. The velocity, initial velocity of this is 2u. The initial velocity of this is u. And this is at an instant of time t equal to 0. Now irrespective of the acceleration, whose velocity is higher? This. So initial stages, this will be ahead of this. It's the velocity that determines which will be ahead, right? So the velocity of this is higher than the velocity of this, so this will be ahead of this, right? However, this has a higher acceleration, so it will catch up with this after a while, right? We want to find the time when it catches up and the distance from A where this particle, lower particle, will catch up with the upper particle. That means let me call this particle P and let me call this particle Q. Initially P will be ahead of Q because of a higher velocity, but because of a higher acceleration, Q will eventually catch up with P. We want to find the instant when Q is able to catch up with P, right? And then we want to be able to find the distance from A when Q is able to catch up with P. Let me solve this problem in the context of relative motion. Let me solve this problem in the context of relative motion. So what I do is, this problem has an equivalent. I choose Q to be my observer. That means as if I am fixing Q, pinning Q down, right? It's as if Q is my observer. So I'm drawing an equivalent situation. I'm drawing an equivalent situation in which Q is looked upon as an observer, a fixed particle, right? Now, if that is done, then the velocity of P would have to be modified. It will no longer be 2u. It will be velocity of P minus velocity of Q. The velocity of P will be relative velocity of P with respect to Q. It's a velocity of P with respect to Q now in an equivalent situation where Q is converted into an observer. That means as if Q is at rest, then the velocity of P would have to be modified. It's going to be 2u minus u. It's the velocity of P as seen by Q, which is 2u minus u. So then the velocity of P would be u to the right as seen by Q, where Q is fixed. Now, what is the acceleration of P? It's not going to be a to the right. It's going to be acceleration of P minus acceleration of Q. So acceleration of P as seen by Q is going to be acceleration of P, which is A, minus acceleration of Q, which is 2A, which is minus A. Minus A means A to the left. I've chosen rightward positive. In my scheme of things, let me say rightward positive and leftward negative. So velocity of P as seen by Q is u. Acceleration of P as seen by Q is going to be A minus 2A. That means minus A to the right, which is like A to the left. Minus A to the right is like A to the left. So acceleration of P in this scheme of things is going to be A leftwards. That's my equivalent problem. Yes or no? Okay. Now, as if A is at rest, Q is a fixed observer, and P is moving to the right with a velocity u, but has a retardation A to the left, I want to find out the next instant of time when P would once again bump into Q. Now that's going to happen here, right? Because in this equivalent situation, P is retarded. So eventually, P will keep moving to the right, but in a retarded state, its velocity will keep getting killed. At some instant of time when P reaches some P prime, its velocity is going to become 0, but its acceleration will continue to be leftwards and A. It will then come back to Q and pay its tribute to Q. Yes or no? Right? Isn't it? So P will once again bump into Q after having completed this journey from P to P prime and then back to Q. So that will give me the time elapsed when P and Q would once again meet. They initially were together, but then they will meet once again after P completes this full cycle. Yes or no? Now I'm not going to reinvent the wheel. Think of this situation, this should be our reference situation. Under the influence of gravity, when I launch a particle with a velocity u, it has an acceleration A downwards, which is g. Yes or no? This particle reaches the highest point, say P prime, right? And the time taken to reach the highest point is u by g, and the time taken to fall back to P is u by g. So the total time of flight, as we understand, is 2u by g. Yes or no? The time taken to come back to P under the influence of this acceleration acting in the opposite direction is 2u by g. Now, would you not believe it's the same thing? Invert this. Make this horizontal. Make this horizontal. So then it's like u to the right and A always to the left. Right? So time taken to come back to this point, total time of flight, equivalent to a total time of flight is going to be 2u by A. Yes or no? Is going to be 2u by A. Yes or no? Right, so the time is going to be 2u by A. Time taken to do this, like it happened here, 2u by G, it's going to be 2u by A. Yes or no? That's the time after which Q would catch up on P. Q would catch up on P. Now, in this time, now I've exploited the equivalent situation to find the instant when Q would catch up on P. Now using this, now I can forget all about the equivalent situation. Let me go back to the mother situation. In this time, let me find out the displacement of P. Right? In this time, in an interval of time t equal to 2u by A, the Q reaches this point where it is overtaking P, and in this time, the displacement of Q is going to be, Q has a velocity u to the right, so u into t, which is 2u by A, right, plus half of 2A into t squared, which is 2u by A whole squared. Yes or no? ut plus half A t squared. Does it make sense to you? So that's the displacement from A when Q is able to catch up on P, whatever this turns out to be. 4u squared, so 6u squared by A. 6u squared by A. Let's also do it without relative velocity. Let's also do it without relative motion. Clear? Got me, no? Can I remove the clutter from here? Let me forget this equivalent situation. say at an instant of time t, both P and Q undergo the same displacement S. P and Q once again meet at this point t seconds from A. T seconds from A. That means t seconds from A, they must have undergone the same displacement S to the right. So S that P undergoes in t seconds is going to be 2ut plus half of AT squared, right? And that must also be the displacement that Q undergoes in t seconds, which is u into t plus half of 2a into t squared. Yes or no? Again, you can, t could be 0, which is an initial instant when P and Q were together. So you can cancel t from both sides because t is not 0. We are not seeking t equal to 0. The other instant of time when you solve from this is going to be 2u by a. Again, as you can readily see. Cancel 1t. 2u by a is what you get. Yes or no? And then once you have t equal to 2u by a, you can plug in t equal to 2u by a here, or you can plug in t equal to 2u by a here to obtain the point where they once again bump into each other. The displacement of a body from a reference point, let's say along the x-axis, this is a reference point which is the origin. At an instant of time t, the particle is at P, which is x0 at an instant of time t. X is a function of time for a particle, let's say, moving along the x-axis. X is in meters, t is in seconds, and it's given that x varies with time as root x equal to 2t minus 3. Root x equal to 2t minus 3. Okay? We want to figure out the point where it is at rest, whether it's accelerated or not, and let's go on to check on. Let me square this. For convenience, x is 2t minus 3 whole square, right? What would give me the velocity? Velocity is given by dx dt. Now, one thing, that means if I want to differentiate 2t minus 3 whole squared with respect to t. So first of all, this square with respect to this, right? L square with respect to L will give me 2L, right? So first, the square of this with respect to 2t minus 3 is going to be from chain rule 2 into 2t minus 3, and then 2t minus 3 with respect to t is going to be 2. Do you all understand whatever I have done here? Chain rule, right? So which is like 4 into 2t minus 3. Yes or no? So dx dt is going to be 4 into 2t minus 3. That's the velocity at various instants of time. The particle would be at rest at an instant when v becomes 0, right? Evidently, v is 0 at t equal to 3 by 2. That means the particle is instantaneously at rest at t equal to 3 by 2 seconds. The particle is at rest. V is 0 at t equal to 3 by 2 of a second. Yes or no? Got me? Now, let me look at the acceleration. dv dt is the acceleration. Acceleration is dv dt. If you differentiate this, so it will be 8, right? This will be 0. So that's going to be 8 meters per second square. So the particle has a positive acceleration. Its velocity is increasing with time. Yes or no? It's a case of constant acceleration. Got me? So options. Option A, it's at rest at t equal to 3 by 2. Option B is accelerated. So A and B are correct options. A and B are correct options in this case. Shall we proceed? Number 8. Number 8. There is a particle which is thrown up from the ground, let's say with a velocity u. It experiences a constant air resistance which can produce a retardation 2 meters per second squared opposite to the direction of velocity. The ratio of time of ascent, it reaches a highest point. This particle reaches a highest point P. Ratio of the time of ascent, t1 seconds, let's say, is the time it takes to reach the highest point where its velocity is going to become 0, right? And t2 is the time it takes to fall back to A. We want to find t1 by t2 given that g is 10 meters per second squared and the retardation in a direction opposite to the velocity is 2 meters per second squared at all times, right? Okay, please understand this problem now. Now, when it's going from A to P, P is the highest point because the velocity has become 0. If its velocity had not become 0 at that point, it would have gone up further. Right? Please have a seat. Now, during its journey from A to P, its velocity is upwards, right? Its velocity is upwards, but g is anyways downwards at all times. And there is a retardation which is velocity averse. There is a retardation which is velocity averse, which is air resistance, right? It is not dependent on the direction of g, it is dependent on the direction of v or velocity, right? Same thing. So there is A acting downwards because v is upwards. In its journey from A to P, v has been upwards all the time. So the retarding acceleration would be A downwards, yes or no? That means in its journey from A to P, it effectively experiences g plus A downwards, yes or no? It experiences g plus A downwards. That means its effective g is g plus A. It's like g has got modified into g plus A. I can use the same set of formulas for motion under gravity whereby I replace g by g plus A, right? Now, for a moment, say if this height is h, and suppose even during the downward journey from P to A, that is not happening, but for a moment imagine that even during the downward journey from P to A, the acceleration is g plus A downwards. Just imagine, only for a little while, that it's a case where the particle goes from A to P and P to A with this being g effective all the time. Although when it is coming down, A is acting upwards, because when it is coming down, air resistance is upwards and it's going to be A upwards. But forget that for some time. Forget all about that. If it is g plus A downwards in a full trip from A to P and back to A, if it has been g plus A downwards, then time taken to go from A to P must be the same as time taken to come from P to A, with g effective being g plus A downwards, yes or no? Right? Which means, if that was the case, if it was g plus A all the way from A to P and back to A, then the time taken to go up is the same as time taken to come down. Let me find out the time it takes to come down, because it's easier to do that computation because initial velocity at p is 0 when it's on its way down. And therefore, h is ut plus half at squared, u is 0. So h in its journey from p to a would have been, say it took t1 seconds to fall back to a. It took t1 seconds to fall back to a. Right? So h must be half of g plus a into t1 squared. Yes or no? Where t1 is the time. Suppose the acceleration was maintained at g plus a. Then the time taken to fall back to a would have been half of g into t1 squared. H would have been half into g plus a into t1 squared. Yes or no? As if for the full trip a to p and back to a, the g effective has been g plus a downwards. Then can I not say the time taken to come from p to a is t1 seconds and h is given by half of g plus a into t1 squared? What? Now, therefore, if t1 seconds is the time taken to go from p to a, if t1 seconds is the time taken to go from p to a, with g plus a acting downwards, what should have been the time taken to go from a to p with g plus a acting downwards? t1 seconds. Instead of g being g, it is g plus a. So it's the same time. Yes or no? If t1 seconds is the time elapsed from p to a, then t1 seconds must have been the time elapsed from a to p. So now my interest was in t1 seconds, the time taken to go from a to p. Yes or no? So the time taken to go from a to p is very clearly root 2h by g plus a. And I just imagined the particle to fall back to a with the same acceleration with a view to have an ease of computation of the time it would have taken to go from p to a, which would have been easier to calculate. Do you understand why I took that departure? Right? So t1 seconds, which is the time taken to go from p to a under the influence of g plus a downwards, would have been the same as the time taken to go from a to p, t1 seconds, under the influence of g plus a downwards. So far so good, right? But now, the actual time taken to go from p to a. The actual time taken to go from p to a. So when the particle, so this now looked upon as a to p. A to p. P to a calculation was fictitious because a to p would have been the same time as p to a. Right? Now, from p to a actually, from p to a, at p the velocity is 0, g is acting downwards, the particle is moving downwards, it develops a downward velocity, so force of resistance, a resistance is going to be upwards, and therefore there would have been, I'm sorry, this is g downwards, and a would have acted upwards. So this is like equivalent to having g minus a downwards, equivalent to having g minus a downwards, yes or no? Right? And suppose it took t2 seconds to cover this journey, then this is h units, then can I not say h is half of g minus a into t2 squared? Can I say all of this? Right? So t2 would have been root, yes please? Because a resistance is producing an acceleration a upwards. When it is going down, g is anyways acting down, but a resistance is producing an upward acceleration a, it is opposite to the direction of velocity. Right? So if resultant of this g and this a is going to be g minus a downwards, as if now gravity has become g minus a. No? It's a g downwards and a upwards is like g minus a downwards. So it's as if g effective is g minus a. So h would be half of g effective into t squared.
Is the acceleration produced in the particle that's going on?
Is going downwards. Particle is going downwards. When it is during its descent, the particle is going downwards. So air resistance is acting upwards. This is now for the actual downward journey. Right? So T2 is this. Yes or no? T1 is this. T2 is this very clearly. T1 by T2 is root g minus a by g plus a. G is 10, a is 2, right? G is 10, A is 2. So 8 divided by 12. So root 2 by 3. Ratio of the time of ascent to time of descent is going to be root 2 by 3. Have I confused you? Then shall I try harder? No.
We could use V is equal to U plus AT.
Hmm.
P minus U is equal to minus AT. Then minus with the parallel and this AT. And the A acceleration, if I consider G as 10 and A as 2, then it would be about like U is equal to 12t.
Hmm. U is 12t.
Yeah, so because V is 0 when it goes up.
Hmm.
Point.
So when it is going up, it's G plus A downwards. Okay.
Yes, and when it comes down, V here U is 0.
Okay.
Final velocity is again like 8.
80. Okay. When it hits the ground.
Yes.
Right.
T is then and
V squared, V is proportional to square root of H. V squared is proportional to H. V squared is 2GH. So V is proportional to square root of H. Isn't it? So that's where it's going to come in. Got me? Shall we move? Are you certain about everything that I have said here? Hmm? Now, in a plane, what's given is the actual trajectory of a particle in the xy plane. In the xy plane, there is a particle which is executing a motion along a trajectory given as follows. It goes from this point A, actual trajectory of the particle, to this point B. This is 4 units. This is 3 units. And then it goes along this line where this angle is 40. So this is 30. Then it goes along this line and it goes to a point P with coordinates 4, 1. This is 45 degrees. This is 45 degrees. Okay. Now and this point A is 0, 4, coordinates of this point. We want to find, when it's at P, the angle between the directions of its average velocity and instantaneous velocity. At P, while it is at P, it is headed in this direction. So this is the direction of its instantaneous velocity, isn't it? This is the direction of its instantaneous velocity. Isn't it? When it's at P, it's going in this direction. This, therefore, is the direction of its instantaneous velocity. Yes or no? Now, what is average velocity? Average velocity is total displacement by total time. Average velocity is total displacement divided by total time. That means delta S is the net displacement of a particle, right? It does not depend on the path actuals. It depends only on the initial point and the final point. It does not matter what the particle has been doing between the initial and the final points. So when the particle eventually goes from A to P, this might have been the actual trajectory. It does not matter. The net displacement is this. AP is the net displacement. That means this is the displacement direction. Delta S, change in position, displacement, right? So this must be the direction of the average velocity, delta S, which is the displacement of the particle from A to P. This also gives me the direction of the average velocity. So the average velocity is directed this way. The instant velocity is directed this way. I want to be able to find the angle between the instantaneous velocity and the average velocity. This angle is what I'm seeking to find. You know what I'm saying? This is the direction of the instantaneous velocity. This is the total displacement, and in the direction of the total displacement is the average velocity. The average velocity is along the direction of total displacement, yes or no? Right? So angle between the direction of average velocity and instantaneous velocity. That means this is the angle that I am seeking to find. Yes or no? Do you all understand this idea? Or have I bothered you with this? No? Okay. Now it's about very mundane trigonometry, geometry. Suppose this angle is alpha. Suppose this angle is alpha. What is tan alpha? Tan alpha is 4 by 3. Now, from now on, this should get into your standard values of angles. When tan alpha is 4 by 3, alpha is 53 degrees. Alpha is 53 degrees. This value is used very often, so I want you to remember this. Alpha is 53 degrees. That means sine alpha is 4 by 5 for 53 degrees, and cos alpha is 3 by 5 for 53 degrees. Tan alpha is 4 by 3, alpha is 53 degrees. From now on, this 53 degree angle is a standard angle. Okay? Okay. So this we know is 53 degrees. Okay? Now, evidently, this then, this plus this is 98? Yes or no? This plus this is 98. So this must be 82 degrees. Yes or no? This must be 82 degrees. Clear? 180 minus 98. So that makes it 82 degrees. Now, what is the length AB? Can you tell me the length AB? Root 4 square plus 3 squared? 5. AB is 5. Can you tell me the length AP? Distance formula. Distance between 0, 4 and 4, 1. 0, 4 and 4, 1 means distance formula 4 squared plus 3 squared. That is also 5. Yes or no? That means AB is equal to AP. AB is equal to AP. It's an isosceles triangle therefore. And if this angle is 82 degrees, how much is this? 82 degrees. And therefore theta is 82 degrees. This theta is 82 degrees. The direction between the average velocity and the instantaneous velocity of the particle is 82 degrees. Yes or no? Number 10. A tiger runs a 100-meter race. God knows with whom. Accelerates for 1/3 the total time and then moves with uniform speed. The total time taken by the tiger to run 100 meters if the acceleration of the tiger is 8 meters per second squared. The acceleration of the tiger is 8 meters per second squared. Initially, it moves with constant acceleration and then moves with a constant velocity to cover this 100-meter race. Now let me do it graphically. Velocity time graph, velocity in meters per second, time in seconds. Obviously, it starts from rest. And it accelerates at a constant value. If the particle has a constant acceleration, then its velocity time graph will be a straight line, and the slope of that straight line will give me the acceleration. Yes or no? Right? So, initially it has this, where if this angle is theta, then tan theta will measure the acceleration. Yes or no? Slope of this line will measure the acceleration. And then for some time it moves with constant velocity. And in the process, this entire area would be 100 units, which is the total displacement. Area under the velocity time graph is the total displacement, which is known to be 100 meters, which is known to be 100 meters. Yes or no? Right? Very simple. it's given that this, suppose the total time is capital T seconds, then this is T by 3 seconds. This is T by 3 seconds, yes or no? Right? And tan theta is 8. So this length divided by T by 3 is 8. Yes or no? This length, tan theta is this length, divided by T by 3 is 8. Isn't it? So this length must be 8T by 3. Yes or no? Because this length divided by T by 3 is acceleration 8. Yes or no? Do you all understand this? Now, the total area. Area of this triangle, how much is it? Half of base T by 3 into altitude 8T by 3. Right? And this length is 2T by 3. So area of this rectangle is 8T by 3 into 2T by 3. And this must be the total displacement, area under the velocity time graph, which is given to be 100 meters. Yes or no? You can solve for T. You can solve for T. Yes or no? How much does it turn out to be? 3 root? 3 root 5? Okay. Let me tell you another way of looking at it, if you don't mind. This is one way to look at it, right? Let me tell you another way to look at it. Graphically only, but just for the heck of it. Assuming you've registered the ideas here, right? Area of this triangle, which is this. Area of this rectangle, which is this. That's the total area under the velocity time graph, which measures the displacement given to be 100 meters. Right? For fun's sake, let me give you a different view to this. Can I remove the clutter from here? Now, let me break this into two equal intervals. T by 3 and T by 3. Right? This is T by 3 and T by 3, and this is T by 3. Three equal entities. Right? Now, do you realize that if the area of this rectangle is 2A, the area of this rectangle will also be 2A, and the area of this triangle will be A. Because they have the same height and the same base. So the area of the triangle will be half the area of the two rectangles, yes or no? Right? That means the area of the triangle is 1/5 this total area. The area of the triangle, isn't it? Because these areas are in the ratio 1:2:2. So this would be 1/5 the total area. That means this must be 1/5 of 200, 1/5 of 100. That means 20 meters, yes or no? This area must be 1/5 the total area. 1:2:2. So this is 1/5 of the total area, which is 100. So this is 20 meters. Therefore, the area of this triangle is 20 units. That means half of T by 3 into 8T by 3 is equal to 20. Will give you the same value of T. Got me? So there is an elevator which has an acceleration A upwards. There is an elevator which has an acceleration A upwards. Ball, huh? Sorry for this, huh? Unintended. A man in a lift ascending upwards with an acceleration A throws a ball vertically upwards with a velocity V. I mean, that would have been too light, yeah. With a velocity V with respect to himself, because when he's moving up, he has a non-zero velocity. So with respect to the man, that means with respect to the elevator, he has a velocity V upwards. You know what I'm saying? And then it goes up and eventually it has to fall down. And they say it takes T1 seconds for the man to catch the ball. Right. Huh? So what happens is, while the elevator is going up, it takes T1 seconds for the ball to be caught by the hand at A. Right? Okay. So let me explain this part. What should T1 be? What should T1 be? I'm going to solve this problem with the notion of relative velocity. I'm going to solve this problem with the notion of relative velocity. That means I will imagine the man and therefore the lift to be my observer. That will be my frame of reference. I will treat the man plus and the elevator as my frame of reference, as my observer, as if I'm pinning them down, as if I'm pinning them down. Then on launching the particle from A, well, it's already given. So if I'm fixing the elevator and the man, pinning the elevator and the man, then it's as if I'm imparting this ball a velocity v with respect to the man or the elevator, which is given to be v. This is the velocity with respect to the man or the elevator, which is v anyways, right? Now, the acceleration of the ball when it's released, it's at the mercy of gravity. When I throw it up, it's at the mercy of gravity. It doesn't understand the acceleration of the elevator. It doesn't understand the acceleration of the elevator. So its actual acceleration with respect to the ground is g downwards. So now A is like a fixed point now. A is now like a fixed point. The hand which is chucking the ball up is like a fixed point. And the velocity with respect to A is v. Now, if I am fixing A, then the acceleration of the ball which is moved up should be acceleration with respect to A. If I am looking at things with respect to A, the acceleration of the ball which is actually g, now should be modified, because I am looking at it from the perspective of the observer at A. It should be acceleration with respect to A. The acceleration of the ball would be acceleration with respect to A. See, A actually has an acceleration A upwards because it's integral with the lift. And the particle when it is released, the particle P when it's released, has an acceleration g downwards. So its acceleration with respect to A, it's going to be acceleration of P minus acceleration of A. Its actual acceleration would be acceleration of P, which is g, minus acceleration of A, which is A upwards, means minus A downwards. A upwards is like minus A downwards, which is g plus A downwards, yes or no? So acceleration of P as seen by the elevator is, or by the point A, is g plus A downwards. So this is an equivalent situation where v is the velocity as seen by A, initial velocity of the particle being chucked as seen by A is pinned, A is fixed, and therefore the velocity of the particle P would no longer be looked upon as g, would be looked upon as acceleration of P with respect to A. A has an acceleration A upwards, whereas P has an acceleration g downwards. So what's the acceleration of P with respect to A? G plus A downwards. So everything from the perspective of the lift frame of reference, that means as if the lift represented by A is a fixed entity, as if the lift represented by the point A is a fixed entity, the particle P then is launched up with a velocity v, and it has a constant acceleration g plus A downwards, yes or no? In this equivalent situation, A is like a fixed entity. It's being converted into a frame of reference. And in this case, the velocity with respect to A is v upwards and an acceleration g plus A downwards. So for it to come back to A, the time taken is going to be 2u by g. G means now g effective. G effective is g plus A. So 2v by g plus A. 2v by g plus A is going to be T1. T1. Time taken from A to reach the highest point under the influence of G plus A downwards and come back to A. That means being caught by A is going to be 2V by 2U by G effective, isn't it? The total time of flight, 2V by G plus A. Is it confusing? I'm assuming that. Otherwise, nothing can be said. You know, it's going to collide and then its velocity will change and it will have an. I'm assuming that, you know, it's able to reach a height which is not hitting the ceiling of the elevator. We'll assume that. Because since we don't have any data which otherwise says things, so we'll assume that it's not hitting the ceiling of the elevator. Right. So time taken is 2V by G plus A. Yes or no? What have I done here? The particle was actually launched with a velocity V with respect to the hand A, which represents the lift. Because it's integral with the lift, it represents the lift. The point A actually has an acceleration A upwards, which is the acceleration of the elevator. Right? Now, t1 seconds, actually the point A is going up, the particle is also going up, and the particle would be caught by A after a while, which says t1 seconds. What we did was we converted this situation into an equivalent situation where I looked upon A as my observer. So if A was my observer, the velocity of the particle that was launched should be the relative velocity with respect to A, that's given to be V anyways. Right? The acceleration of P now, the particle that is being launched, should be acceleration with respect to A. And what is the acceleration of the particle with respect to A? When released, when left by A, it has G downwards because it's solely at the mercy of gravity. And acceleration of A is anyways upwards. But in an equivalent situation, I would look at acceleration of P with respect to A, which is G plus A, where A is fixed and P now has an acceleration of P minus acceleration of A, which is G plus A downwards, yes or no? So in the equivalent situation, A is fixed. The particle is launched with a velocity V with respect to A and has an acceleration G plus A downwards. So now for it to come back to A, time taken would be twice the initial velocity divided by the effective gravity, which is G plus A. Yes or no? Do you precisely understand everything that I have said here? Now, when the lift comes down with an acceleration A, again, I'm solving the problem in the lift frame of reference. This is the point A. This time, the elevator is moving down with an acceleration of A, and the particle is once again launched with a velocity V with respect to A. Relative velocity with respect to A. So now, in this equivalent situation, A actually has an acceleration A downwards. The particle P, when released, has an acceleration G downwards. It doesn't understand the lift then, right? So acceleration of the particle P as seen by A. So if I'm fixing A, then acceleration of P should not be G, should be acceleration of P with respect to A. Acceleration of P with respect to A is going to be G minus A, right? So in an equivalent situation, P is launched with a velocity V from as if A is a fixed point, and then has an acceleration G minus A downwards. Effectively, gravity becomes G minus A. So the time taken for it to come back to A is T2 seconds, which is 2V by effective G, which is G minus A. Yes or no? Where V is the relative velocity with respect to A that the particle was launched with. So G plus A, as you can see, is 2V by T1. G plus A is 2V by T1, right? And G minus A is 2V by T2. To find A, do we need to find A here? So let me subtract these two. So if I subtract these two equations, 2A is 2V into 1 by T1 minus 1 by T2. If I subtract this minus this, 2A is 2V into 1 by T1 minus 1 by T2. That will give me the value of A. And if I want to find the value of v, if I add these two equations, then I end up getting 2g equals 2v into 1 by t1 plus 1 by t2. So that will give me v equal to g t1 t2 by t1 plus t2. v will turn out to be g t1 t2 by t1 plus t2. Check with what's required. I am not sure what all is required. So velocity v of the particle with respect to the elevator, g t1 plus t2 by t1 t2, which is this, option A is right. Acceleration A of the lift is g into, yes, so you can find the acceleration of the lift. You can plug in the value of 2v there. Does it turn out to be g into t2 minus t1? It does, right? I mean, in fact, right away I can say g plus a into t1. G plus a into t1 is g plus a into t2. G minus a into t2. Both are equal to 2v. And then t1, a into t1 minus t2, g into t2 plus t1, right? So that makes option C also correct. Option B is correct. Option C is correct. Option A, the acceleration of the ball with respect to the ground is g when it is in air. True or not? Yes, true. A is true. With respect to a ground observer, the acceleration of the particle which is released will be g downwards. With respect to the elevator, it's going to be g plus a and g minus a as seen in the situation. So option A is right. Option B is right. Check with option C. Check with option C.
So B, how is B then?
Oh, B, no, D is right. D is right. V is G T1 T2. V is G T1 T2 by T1. V is G T1 T2 by T1 plus T2. So option D is right. Is option C right? Option C right? Option A is right. Right? So A, C and D. A, C and D. In fact, dimensionally you can see that option D will give me meters per second, but option B is not giving me meters per second. Do you realize that? Because T1 plus T2 by T1 T2 is 1 by second, and G divided by second would be meters per second cubed. So dimensionally anyways B is wrong. Dimensionally option D is right, because it's second squared by second, which is second. Meters per second squared into second will be meters per second. So D ought to have been right, right? Number 12. A particle is moving along the x-axis with a constant acceleration. At t equal to 0, the particle was known to be at x equal to 3 meters. And dx dt at this instant means the velocity. Dx dt is velocity at this instant is plus 4 meters per second. That means 4 meters per second to the right. The maximum x coordinate of the particle is observed 2 seconds later. At t equal to 2 seconds, x becomes x max. That means it can't go further than x max. It doesn't go to the right of x max. That's given. After what time will the particle return to its original position? Now, would you want to believe that the particle is not going further than this? That means at t equal to 2 seconds, its velocity to the right must have got reduced to 0. That means between t equal to 0 to t equal to 2, it must have got retarded, uniform retardation. So it must have had a uniform retardation a to the left, a meters per second squared to the left. That must have been the state. Yes or no? And then obviously it remained a to the left from this point onwards. Starting from rest, it eventually has to come back to the original position. I want to find the time it takes to go from here. Now, would you again hate to believe that this is like gravity looked at horizontally? Instead of g, you have a, and the time taken to reach the maximum height is 2 seconds, and then to come back to this point would be another 2 seconds. So 4 seconds, yes or no? Yes or no? 4 seconds. Look at the whole thing as if make gravity horizontal, and instead of g, you have a. The time taken to reach the maximum height is 2 seconds, and then come back to the ground is another 2 seconds. So 4 seconds. 4 seconds is all that you have. Yes or no? Right? The displacement x for a particle moving along the x-axis, its x coordinate is x at an instant of time t given by root x plus 1 into x minus 1. That's relationship connecting the x coordinate and the instant of time t. We want to find the acceleration at an instant of time t when it's at x. I want to find what its acceleration is. Clear? Okay, let's work through the algebra. T squared is x squared minus 1, right? Or x squared is going to be t square plus 1. Differentiate both sides with respect to time. Chain rule, 2x dx dt, yes or no? Do you understand what I have done here? 2x dx dt, isn't it? That's equal to 2t. Don't understand. Differentiating with respect to time, differentiate x square with respect to time is like first differentiate x square with respect to x, that is 2x, and then x with respect to time. That's chain rule. I want you to go back and look at that session on chain rule one more time in case you've forgotten that. Right? X dx dt is t. That means x into velocity v is t. Yes or no? Dx dt is the velocity v. V is dx dt. How about it? X into v is t. Let me differentiate this one more time. What is the derivative of the product of two functions? Derivative of first function into second function plus derivative of second function into first function. I am seeking acceleration, so I am seeking to find dv dt effectively. I am seeking to find dv dt, right? So let me differentiate both sides with respect to time one more time, right? So derivative of the product of these two functions is derivative of x with respect to time into v plus x into derivative of v with respect to time, isn't it? Derivative of the product of two functions, derivative of x with respect to time, derivative of first function into second function, plus derivative of second function into first function must be ddt of t, which is 1, yes or no? But what is dv dt? Acceleration a. dv dt is acceleration a. Now this is v into v, which is v squared. This is v into v, which is v squared, isn't it? Dx dt is v, so v into v, which is v squared, and dv dt is acceleration a. dv dt is acceleration a, right? So x into acceleration a is 1 minus v squared, 1 minus v into v, which is v squared. But do you realize v squared is t square by x square? V square is t square by x square, isn't it? So v square is t squared by x squared, right? This v squared I seek from here, t squared by x squared. I plug into this, so which is like x squared minus t squared by x squared. But what is x square minus t square? X square minus t squared is 1. X square minus t squared is 1. So this is 1 by x squared. That's x into acceleration a. So a must be 1 by x cube. A must be 1 by x cube. 1 by x cubed. X into a is 1 by x squared, a must be 1 by x cubed. Got me?